So change in temperature is the same as delta P, right? So it's delta T, delta P, the same thing, but it's going in. That's at the level of the mixer feed minus what we have here should give you delta T. Since this one is not enough, one heater is not enough, we had 2011 here, and here we had 2686. It's still not enough. We need it around 3000. In as much as I can manipulate it, but you don't want to stress the equipment. Remember, asset integrity. Then you take the second one, model palette, drag and drop, energy stream, then heated mix feed. Now what is entering the inlet is going to be the outlet of this is the inlet of this. So what is coming out from this first heater is the input of this second heater. So I'll say heated reactor feed. So we have heated mix feed here from the mixer, then heated reactor feed from this other reactor. So it heats parameter, same thing. You're looking at only delta T. Delta P will automatically calculate itself, or maybe they can ask you to input it, but you make sure that the change in pressure is not too much, because if the change in pressure is too much, your system is in trouble. So I'll take delta T, which is the same as what is going out minus what is coming in. It's basic math. If I have let me see, calculator. Let me open the calculator app. So we're looking at delta T is, I want to have 361 Fahrenheit here. So you have your temperature, right, that you need at that level. Maybe you need that 3361 Fahrenheit, right? You need it at that end, but you have 2686 minus that 2686, 675. That will give you delta T. Delta T is change in temperature. Same thing for delta P, change in pressure. Now we have heated our feed to a temperature that we require. So the next thing is we need a reactor. Remember, if you did not take this stage where you set your reaction, your reactor, there is nothing working at the level of the reactor, right? So you come to your model palette and you take reactor, or you type reactor, or you just simply come down here, click reactor. Now that's why I said it. Since there are so many equipments, there's a lot. I mean, there's so much to explain. I cannot do it all in one video. I'll just focus on my simulation. I'll just focus on your simulation. Now, so here I'll have continuous flow, plug flow reactor, convection reactor. If you remember, maybe if you remember LNG, yes, the course I think was taught to us by Mr. Kiven. And if you remember this course, I think petroleum refinery, voila, you see things here like this breaker. If you focus on the course, you see this, a vis breaker. If you want to learn how it functions, read that course. Those things, fluidized catalytic cracker. This is it here, fluidized catalytic cracker. I mean, there are so many reactors, there are so many hydrocracker. It's in the course. Catalytic reformer and neutralizer and all of this. I mean, so here we need let's see. Yes, we need a conversion reactor. So I will drag and drop. You see, right? We need a conversion reactor because we want to convert that thiophene to a different substance, right? So I'll double click on it. So I'll looking at this. we need the inlet. The inlet now is our heated reactor. So here the inlet, I'll choose that heated reactor. Now energy here is optional. I just decided to put it because I know these systems require energy, so it's optional. You can leave it blank, you can put it as pen or calculate it manually for you. Then you need an outlet, a vapor outlet. So I'll say reactor gas out, reactor liquid out, right? Then I'll come to parameter delta P. Your change in pressure should not be too much. If your change in pressure is too much, you have a lot of problems. I have not sized any of the equipment, so you could be working with a particular range, right? You can size your equipment vessel volume. The document has not given us a vessel volume, and equipment sizing is another topic on its own. They have not given us the liquid volume that the reactor can take, vessel volume and liquid volume, but I've set a level to 70%. Aspen will automatically assign values to it based on your input. Next, very important for a reactor, you take reactions. Remember, you come here, this reaction set, you select set 1, and for that reaction set 1, you automatically input this reaction here. Remember our reaction at the level of properties, right? Here, if you don't put this here, when you come to your simulation environment, you will not have it. So you have the tiophene, hydrogen, H2S, which is the product obtained, and butane, right? When you select it, it automatically converges for you. So here you can always check. Remember, at the end of the day, we are trying to clean this diesel feed to remove sulfur desulfurization. Remember, look at this diesel feed here, composition. What is the sulfur percentage? Hydrogen sulfide here is 0.3142. Remember, like I said, I can add maybe something here at the level of tiophene. Let me see if it's going to disturb my simulation or something. Let's just take 0. Maybe it can disrupt the whole simulation. 0.23. Take enter, then I normalize it. I take OK. Oh, our simulation converges. Wow, interesting. The results will definitely change. Right now we have tiophene and we have hydrogen sulfide. You're trying to clean tiophene, you're trying to clean hydrogen sulfide, so always have that at the back of your mind. Always come back and check. So here, when you click on this, you see that the molar flow is 0, so you're not concerned with this. You're concerned with this one where we have 4,225. There's gas flowing here, but there's no liquid flowing here, therefore the conversion is working. But now remember, because of high temperatures, they are obtaining only gas. Look at the temperature here, 3,231. That's increased, therefore we have more gas than liquid. So it's okay if there's no liquid here. You can just put a tank, should in case, like I've put a tank here. You can put a tank here should in case there's any liquid form in the nearest future. So I mean, it's a whole process. So we're at the level, we just finished with the reactor. Now this is our focus, composition. You see the change. Tiophene here is 0 because it's our tiophene that has reacted. You get, tiophene is 0. Hydrogen sulfide has reduced from that 0.3. You see the way it's reducing. If tiophene here is 0, it simply means you have succeeded to remove some sulfur compounds from your simulation. When you're looking at this, so the sulfur, you don't have it directly, you have it in the form of hydrogen sulfide. Sulfur removed from tiophene, hydrogen sulfide here. So the next thing is to remove this hydrogen sulfide.